Okay, welcome to GADEP seminar. So today we have Ilia Zharkov, who is going to talk about tropical Hodge conjecture for Abelian varieties. So Ilia, please.
All right, thank you for the invitation. It's nice to be both in China and in Rio at the same time, and in Kansas. Okay, so it's basically what Maxim Kontsevich told. I mean, I had several discussions with him maybe like 12 years ago or something like that. And so that's what I'm gonna convey here. And all right, let me move. So that's the plan. So I'll say a couple of words about what's the classical Hodge conjecture for Abelian variety, what's known in those cases. I'm not be up to date, as I said, so it's been like 10 years or something since I was thinking about it, so I apologize for that. Then I will say what's the tropical version of that thing is, and then how Kontsevich proposed to give a counterexample to the tropical version of that. And also say what, what's the counterexample, what the tropical how the tropical counterexample would give a classical counterexample. All right, so I'll start with like a first slide is for just a brief introduction to subject. So it's the Hodge conjecture is about X is a smooth projective variety over complex numbers. And then we denote the group of algebraic cycles. It's a vector space. We make it with Q, with coefficients in Q, because it's known conjecture false with Z coefficients. So and we also look at the Hodge classes. Those are the cohomology classes, which are both rational classes, and they also PP type, namely that they are, as in terms of Hodge decomposition, they are of in the middle column. Every algebraic cycle, of course, if you just take its Poincare dual, then is that me? So if you just take Poincare dual, then it's called a cycle class map. So for every cycle, we can associate a class, a cohomology class, and obviously if the cycle has a integer or rational coefficients, then it's going to be a rational class. And it's very easy to say if it's a holomorphic submanifold, then it's going to give a PP type by integrating the forms. Any other forms would vanish, any other types of form, the integrals. Actually, the forms would vanish already, not just the integral. So, okay, so what's known about this conjecture in general? Except the two obvious cases, there is one more, a little bit less obvious case. Of course, the top and the bottom thing is, so P is a complex dimension here. So you can obviously nothing to say about the zero or top part, and Lefschetz hyperplane theorem tells us that it's true for P equals 1, and the Lefschetz hard Lefschetz, when you change the PP into n minus p cycles, this reflection of the Hodge diamond will tell you that it's also true for the complementary dimension. So the first non-trivial case is when a dimension is 4 and we are in the middle. So 2 cases, the first non-trivial. So the easiest, what happens? What's this red line doing here? Do you guys see the red line too?
Yeah, I see the red line. I don't know what it is.
What happened? Why did I?
Maybe with your mouse you have written something, but I think it doesn't matter.
Why bother me?
Okay.
It seems like something significant is crossed. So more. Anyway, so let it be. So the first non-trivial case is the four-dimensional, as I said, and the easiest varieties we can deal with is the Abelian varieties. And if you take a generic Abelian variety, then it doesn't have any classes except the powers of the polarization. So you're gonna go to some special varieties like, but even for some like very special like Jacobians and stuff like that, the conjecture is known to be true. So the prime varieties and stuff like that. So for any like geometric abelian varieties, people come up with actually finding those cycles which represent all the cohomology. The first example which people cannot find representing cycle are the so-called varieties of Weil type. So, okay, in general, what's the abelian variety? It's the complex numbers. It's a vector space C to the 4 and 4 dimensions modulo some lattice in it. And the condition of being abelian variety, namely that it has an embedding into projective space, namely that there is a class, which is the first Chern class of the hyperplane section, is equivalent to the following. So we actually have a form, this Q-symmetric form on a lattice called E, and the form is called polarization with the two conditions. Well, we can write it as one condition, but sort of it's respect the complex structure, and it's the positive, and it's a symmetric form once you put a J. J is a complex structure here. So if you apply J to one of the variables, then it's symmetric. Then it's, yeah, so anyway, so symmetric and positive definite, we can put it all in one condition. This is called a Riemann relation. So essentially this linear algebra. Now we want to talk about special, this is a general abelian varieties. So the special abelian varieties of a Weil type, they come with so-called complex multiplication. So there is some quadratic extension of Q of some field of degree 2 over Q, and which acts on this variety on X, and with some conditions, and namely the condition is the following. Okay, so let me say it this way. So once it acts on it, it also acts on a tangent space at 0, and so it acts on and a tangent space of 0 is like a 4-dimensional complex space. So, but it also becomes a vector space over this extension over K because it acts on it. And the condition that it actually gives the eigenvalues are split into into two pairs, two equal sizes. So like this minus square root of d acts as minus square root of d minus square root of d, and square root of minus d and a minus square root of minus d. So two of them are square root of minus d, and the other are the complex conjugates to that. And the third condition is that it should preserve, well, it should act as D on this polarization form. This is not really a condition because this we can actually change once we have a polarization and this action, then we can then this act is a D or as minus D. So we just split this thing into two parts, and then we just add the skew the minus D part. We're just gonna increase the E. So it was symmetric positive definite, and once we increase it with values, and it's still positive definite. So this is not really a condition. We can change the E a little bit. Okay, and then the statement is that you actually have two more classes in H22, which are Hodge classes. And where these two classes come from? These classes come from the following things. So you will look at this vector space gamma as a K vector space. You take its top exterior power, that's the one-dimensional K vector space. This is this left-hand side here. It's one-dimensional over K. It's a top exterior power. And so it becomes two-dimensional over Q. And it turns out that the way how it sits inside this lattice, which is gamma 4, is actually sits inside the Hodge classes there. So there are two-dimension more of the Hodge classes for those. And the question is whether they come from algebraic cycles or not. Okay, there is one more ingredient. One, maybe I'll skip it, but there is this. You can form this. You can make this Hermitian form out of the data by this formula, and then one more kind of discrete parameter is you can look at a determinant of this Hermitian form. Of course, it's defined up to conjugation, up to whatever left multiplication and right multiplication by the transpose conjugate. So it's determinant is well defined, not in Q star, but it's well defined modular the squares of the elements from the fields. So this is a huge group. It's infinitely generated, but all the elements are index 2 or order 2. Sorry, order 2. So it's a lot of elements. All of them are order 2, but that's a huge group, and you take an element here. So for any, now this, then Van Giemen, I think it was Van Giemen, at least this is I've read in his paper. He showed how given any integer, square-free integer, and any this element in this quotient, in this determinant, then you can actually build a four-dimensional family of such varieties. And there are many of them because you build essentially up to, I mean, the point is that how you put the integral cohomology inside the rational first cohomology. So you need a choice of the lattice inside the Q vector space. And that sort of defines you up to isogeny. So all of them are isogenous. So as I said, so this isogeny choice is more or less a choice of the integral lattice inside the Q vector space. Okay, so Weil proved that if you take a generic member of any such family, then you actually get Q cube. You may get higher than cube, but that's actually very special. And on the other hand, that if you get higher than just a Q, so the generic four-dimensional abelian varieties would have Q for the 2-2 type, for the two for the Hodge 2-2 classes. And once you get higher, then Munin and Zharkov, they prove that that must be from this abelian variety of Weil type. Now, what's known about the Hodge conjecture? At the time when I was thinking about it, like 10 years ago, I think that this was the only known result. So you take this invariant alpha to be 1, and you can take the either you adjoint I or square root of 3 or square root of -3. And the construction are kind of by this Rickshaw, they are sorry, Chatshon. It's not Rick, this is Chatshon. So they also kind of construction some triple cover and looking at some prime varieties. So they're very geometric to find these classes. And then Markman actually told me a couple of years ago that he knows how to prove it for any quadratic extension for this case. But when alpha is not 1, I think nothing is known. And again, Markman construction is again sort of using some Albanese variety for some Kummer surfaces or something like that. So it's very geometric in a sense. Okay, so that's enough for classical story. Now let me move to the tropical version. So what is a tropical abelian variety? A tropical abelian variety is, roughly speaking, well, as a topological space, it's just a real vector space, modulo some lattice in it. There are some conditions on what kind of lattice. So first of all, this real vector space V, it comes with a natural integral structure. So I'm going to call this integral lattice gamma 0. So there is one integral lattice inside this vector field, and there is another lattice, which is a period lattice. And the condition is that you can. So in some sense, if you write the metrics of the other lattice in terms of the first lattice, then it has to be symmetric and positive definite. That's roughly speaking what this condition says. I'll now give an example later on. Now, or in any tropical, I assume people are familiar with tropical geometry, just a little bit at least, because I think IMPA is like a birthplace of tropical geometry, right? Correct?
Yeah. Actually, what I was reading also, it is the Brazil, but not, I think not IMPA. The one of the founders was in São Paulo, I think. I don't know.
Okay, maybe I'm wrong. Okay. Anyway, so I know it came, at least the word came from somewhere from Brazil. So anyway, so there is this topological class which kind of it's a one co-cycle with coefficients in this integral lattice. And what it does, it's if you give me one chain, like if you give me an interval on your variety with integral directions, then the value of this cocycle on that interval would be precisely this vector, which is this interval. So this is a very like tautological class in there. So this class kind of acts on this space which we call PP homology. So it acts by by the following: it takes the an element from the first factor and just move it over to the second factor. So it decreases the power of the first lattice and increases the power. But now it's not integral anymore. So because the gamma one may not be integral, so we end up with some maybe non-integral things. So we have to tensor it with R. And by definition, the tropical homology classes are the kernel of this map. Okay, now I have to say a word about tropical cycles. Tropical cycles, imagine you are on this essentially like a vector space with the integral lattice in it. So, and I'm considering, this balanced polyhedral complexes. And the balanced means, I'll probably give an example next picture, next slide. Balance means that if you look at any codimension one stratum, and you look at a transversal direction, then it see kind of this picture like this three rays, or maybe more than three rays, and the sum of the outgoing vectors, they are integral, so we can always find like a primitive vectors. Some of these vectors have to be zero. That's the balancing condition. Okay, and so this is an example. So in dimension 2. Because I cannot draw more than two-dimensional things. This is like this dotted lines is a fundamental domain of my torus. So my integral lattice is the one which you see, kind of left, right, and up and down. And the period lattice is given by this two vectors a plus b comma b and b comma b plus c. And this symmetry condition actually shows that the first coordinate of the second vector equal to the second coordinate of the first integral vector. That's this symmetry condition. So for that to be an abelian variety. And if you see that actually that's the necessary condition to fit this, if you want to fit this trivalent graph there, the only way you can do it is actually if that b equal to that b over there. Otherwise, it's not fitting there, so it doesn't have any cycles. But once it's this, then there is necessarily this cycle there, and it's called like this polarization cycle. Okay, but the point I'm trying to make is that once you have this cycle, then you can take the map, which is called the class map or the cycle map, which does the following: you take any polyhedron and think of it as a cell, like a singular cell in your X, but endow it with coefficients, which is the volume form along this interval. So my example here says, so okay, so this is my cycle. If you take, BB is this diagonal thing, you endow it with the 1, 1 direction. Then you take this horizontal one, you endow it with this one, and then you take the vertical interval in endow it with this frame 0, 1, the vertical one. And it turns out that, I mean, sort of, it's not obvious maybe, but it's very easy to convince yourself that once you have a balancing, then you can write this chain with coefficients in gamma 0 as actually a cycle with coefficient in 0. So I've explicitly wrote it, you know, this sum equal to that sum. And now the elements here, the first elements are actually elements in gamma 1. Okay, and alright, there is some argument which shows that this, if you want this cycle to exist sort of in a families, then it has to be in a kernel of this map. And now the tropical Hodge conjecture says, okay, let's say the same thing. So every tropical Hodge class is represented by a cycle. Now, if the tropical conjecture fails, then so does the complex one. That's the implication only in one direction, because suppose the conjecture is true for the complex for the entire family of complex varieties which degenerate to the tropical one, then there is some argument which shows that the actual complex cycles, the algebraic cycle, would become the tropical cycle in the limit. And the same thing with the Hodge classes. So if you had a family of Hodge classes which are represented by classical cycles, complex cycle, then in the limit, the limiting Hodge classes would have to be represented by the tropical cycle. And this is the family which you can build from the, if you can start with the tropical family, which essentially like two lattices, gamma 0 and gamma 1, then you can build this Abelian family, one-dimensional, real one-dimensional family of Abelian varieties. Epsilon is the real parameter. And if the tropical Hodge fails for this lattice gamma 1 and gamma 0, then it fails for this X epsilon, for the complex family.
So this is not an algebraic family of Abelian varieties.
No, it's not an algebraic family, but assuming that you can make it algebraic. I mean, you can make this complex. I mean, this epsilon to be complex.
Yeah, but in the limit, it would be gain some complex algebraic variety if it is an algebraic family, no?
I mean, you can make it into algebraic family by taking not epsilon, by taking t like a non-zero complex number. So
I see, okay.
Epsilon non-zero complex number, then it becomes an algebraic family. But that's not the point. But that's not the point. The point is that if you have any family of the classical cycles, then this family would become in a limit this tropical cycle. You don't have to have like an algebraic family for that. Okay, so now let me say a word what the analog of the.
I'm sorry. So is this a theorem due to whom? Is it really a theorem? So it means this direction is a theorem, right?
I think it's the folklore kind of thing.
Oh, folklore. So I mean so this no question about this plus minus. So it's so you mean this so you really want to see a rigorous proof, you know? So otherwise it's still you mean when you degeneration some problem, right? So I mean this is not really rigorous mathematics for me. Yeah.
You can make. I think you can if you. There are lots of people trying to connect this. I mean, there are two questions here. What happens with algebraic cycles?
Yeah.
That I think is kind of fairly easy to say that the family of algebraic cycles would become a tropical cycle. Now the question is what happens with the classical Hodge classes. I believe it's also probably could be made very rigorously that the family of the classical Hodge classes, they become, you know, this tropical Hodge classes. So I would say it's a theorem, but I haven't seen a proof. But so
so there's no written proof, published proof, or written proof.
There are a lot of things published for some cases, like for curves, certainly for some maybe Jacobians and stuff like that. So there are like huge number of people working on this. So if you ask them, like, you know, this Abramovich, you know, Baker, this kind of people, they are like thinking of the tropical like this non-Archimedean point of view. So they've proved lots of things like this, this kind of degeneration statements.
Okay, thank you.
Okay, so let me now forget the classical story and then just concentrate on the tropical side. So, which is an interesting problem by itself in some sense. You can forget the classical Hodge conjecture. Just look at the tropical Hodge conjecture, and then your question would not arise. Right? So, you just want to answer if the tropical Hodge conjecture is true. Okay, so for that, let me say what's the Abelian varieties of the Weil type are. You can think of this Z4 lattice as being kind of this, you adjoin the root of minus d to z, that's like a z squared, and then you take the square of it. And then you look at the polarization, which actually come from very special kind. They come from this Hermitian form. And I'll show an explicit example next time, next slide. Okay, and once this polarization comes from, then you can think of this as this Hermitian form as actually as the symmetric bilinear form which we need to build the period lattice. So that Hermitian form on this two-dimensional kind of I'd say like a module over z adjoint square root of minus d becomes the symmetric bilinear form on z to the 4. And that's what's the our period lattice is. Okay, so there is one more important thing here. So this is like 4-dimensional space of Hermitian forms, right? There are 2x2 forms, and then they are what a transpose equal to the conjugate. So there are like 4-dimensional space of real parameters for this, and it's convenient to kind of make like a formal Abelian group on those parameters. Let me call this group gamma p. P is for parameters, and then if you think about it, that gamma 1, it's like some linear combination with the basis vectors in gamma 2 with the coefficients in those, you know, parameters, because yeah, so we can think of this gamma 1 actually being written as the, you know, vectors in gamma 0 with coefficient in those parameters. So in other words, we can think of this as a sublattice in the 16-dimensional lattice when you take the tensor product. And the implication of that is that now we can think of the Hodge classes used to be in this two wedge products of the period lattice and integral lattice. And now, since we can write this integral lattice as this inside this tensor product gamma 0 gamma 2, then this wedge product, this wedge square of the gamma 1, we can write as a sim, and then plus the wedge and stuff like that. So anyway, so that becomes an element in this lattice. So okay, I'm gonna give you an explicit formulas. So okay, so I'm gonna take the example when d equals 1. Just what to say, it's not important. I'm still not sure what's the alpha is in this example, because it seems to be 1, which makes it sort of non-interesting, because in this particular example, the Hodge conjecture is true by Schoen. but it's still kind of interesting just to find a tropical cycle which represent those two Weil classes. And so, I mean, it's a still interesting computational problem. Okay, so where are we? This parameter lattice, as I said, so just as a formal lattice on the parameter ABC. I'm not allowed to use D because D is a quadratic extension, so I use E. So okay, so in this basis, so I just take the standard basis for the gamma 0, and I can write the other lattice gamma 1 as this matrix of columns, and the condition for it being, well, it's apparently symmetric, and the condition for it to be positive definite is this two things. So the A has to be positive, the top left corner, and you know, the AC minus B squared has to be positive, and actually, but this kind of condition minus E squared being positive actually stronger. So that implies that the top left 2 by 2 matrix is positive. So that's the condition for this to be positive definite. All right, so let me maybe describe how this complex multiplication acts. So you can just check that if you make this transposition, if you make this action, then your lattice actually stays invariant. So this is some easy check. Okay, now I just want to make sure that there are more than one Hodge classes. So one class is kind of stupid. This is just the square of the polarization class. So we just take all possible. So this double index EIJ means that I take the EI wedge EJ. So this is EIJ is an element in a second wedge of the gamma 0, and gamma ij, the same thing, is just I take the wedge of the gammas. That's an element in lambda in wedge 2 of gamma 1. And if I write this explicitly, I mean, okay, I just follow this procedure how you define these Weil classes by taking the top wedge power over the extension, over the field extension, and then think of it as actually Q vector space. Then you come up with these formulas. So this is, I've done some computation. It's kind of long in the form gamma 1 and gamma 0, but it becomes very, very short if you write it as a sim 2 gamma p and a sim 2 of the wedge 2 gamma 0. So D now is an element. D, remember, was this thing over here. So this is a quadratic expression in ABC, ABC. So D is, we can think of D as an element in sim 2 of this lattice of parameter. This capital D. And these two guys are, each individual bracket is in a wedge of gamma 0, and we take the square, it becomes in sim 2. So anyway, on the other hand, if you try to write this polarization class theta in there, that actually becomes a very long expression. So I didn't even bother to write it. It's like the half of the page. So the polarization becomes long in this expression, but the Weil classes becomes short. And it's kind of fun to check that if you apply this element, namely, for instance, you take the this term gamma 1 2 times E1 2. So what you need to do, you kind of, it becomes like gamma 1 over here, and then you plus or maybe minus gamma 2 over there. And then you take all the sum, and it's kind of, it's a huge sum. It's kind of fun to check that it's actually 0. Anyway, now comes Kontsevich with his idea. So first thing, before I try to explain what's the strategy, the idea is to disprove. Okay, it's not to prove the conjecture, it's to disprove the conjecture. So first of all, observation is that if you have a family of tropical cycles, if you have a family, not just a single one, this single one, you cannot say much about where its vertices are. You can move, but the family actually guarantees, like, imagine, so this vertex, this trivalent vertex is kind of, if you look at it, it has coordinates BB. And imagine you kind of start changing your B and C's, your parameters. But because it's sort of balanced and it's integral, that vertex actually has to follow this change of change of parameters. So the point is that the position of the vertices actually kind of behaves kind of rationally over this space of parameters. So that's I think this is a very important observation. So we can actually assume that the cycles have vertices, not just arbitrary somewhere, but they kind of very discrete position of the cycles, of the vertices of the cycle. So this particular vertex has a position BB. Okay, next thing. We're going to consider two abelian groups. So one abelian group kind of represents all these tropical chains, not necessarily cycles. So what's the tropical chains? The tropical chains are, these chains of polygons. So it's a two-dimensional things in four-dimensional space. And they don't have to be balanced or anything. They don't, have to come with a common edge or anything. It's like a singular chains in some sense. It's just a formal group. But we require that the vertices of each polygon is kind of in this lattice gamma 0 gamma p. But because we are modular gamma 1, so we are not on a vector space, we are on a torus, so we have to mod out by the gamma 1. And we also want the edges to be rational slopes. That means that the planes themselves also have to have rational slopes. They have a elementary volume form. Now, the thing is that we can actually subdivide the polygon into triangles and parallelograms. I don't know how obvious that sounds to you, but imagine like you have a pentagon or something, and then you can imagine that you can try to subdivide it into, and it's always possible, right? This is maybe not a trivial statement, but it's true. And the thing is that we want to keep all the subdividing edges still to have the rational slope. The problem which may occur that we may introduce new vertices, and the new vertices may not necessarily be integral anymore. Because imagine like you have two integral lines intersecting, but they may not intersect necessarily at the integral point. They may intersect like at some rational point. So that's the little subtlety here. So the easiest way is just to go over Q. But in principle, if you're trying to do like a computer experiments, then you may just take smaller and smaller, take larger and larger determinants of your lattice points. Okay, that's the first group, just the formal polygonal chains. Now the second space, again, this is just a formal sum of these flags. So you take a vertex, you take an edge, and you take a face, which is what I'm going to call, and the face, by a face I mean an element in this element of the area form. So this is, the face is in second exterior power of the integral lattice. The vertex is a vertex, so it has to live in this quotient lattice, in this 12-dimensional lattice, gamma 0 times gamma p mod gamma 1. And the direction, we really don't need the actual vector, we only need the direction. So we take the projectivization of the, and now since it's a projectivization, it doesn't matter if you I mean, we have to tender it with Q anyway. So Okay. And now this is like a formal sum like the previous one. So this is like the, again, this singular chain kind of things. But except one instance when the flags, if you have two flags which have the common vertex and a common edge, then we can actually add the area elements. So this in this sense, this is kind of linear. Once we have fixed the vertex and a ray from that vertex. Okay, now there are a couple of maps I'm going to discuss. So the first map is from the first group to the second group. If you take any polygon, then, well, any polygon, we agree that we can subdivide into triangle and paragraph. If it's a triangle, then you take, it has 3 vertices. Every vertex has 2 edges at it. So we have kind of six element, 6 flags, right? So vertex, edge, and the triangle itself. So we have 6 for the triangle, and we have 8 for the parallelogram, because we have 4 vertices, and each has 2 rays at it. And we have a volume element, area element, which is the same for all of them. Now, the important observation here that if you apply this map F to the tropical cycles, which are the balance thing, remember, the balancing condition says that exactly like at each vertex, if you take a vertex and a ray, for instance, then you have, for instance, 3 of those flaps around it. And the balancing condition exactly tells you that if you look at the area elements of those 3 flaps, then they sum to 0. And that happens for every vertex and every ray. So if you apply F to the tropical cycles, then you actually get some group of this flags. They're not 0. I mean, we wouldn't call them 0. Even if F2 is 0, it's still a kind of an element there. But it has this last ingredient, F2, 0 in all the possible flags, if you apply it to the cycle. Now, there is a tautological map from a polygon to this group, okay, so if you have a polygon, well, if it's a triangle, then we compute its area. This is just a product of the lengths of the integral lengths of the sides, maybe 1/2 of that. And then we take the volume element, the area element, and we take it square. So that's the map. And if you think about it, this actually coincides with the class map we had on tropical cycles, after we identified this gamma 1 being a sublattice. Yeah. Okay, so there is some thinking, a little bit of thinking involved here. And now comes the punchline. We want to disprove the Hodge conjecture. So we want to say, all right, so we want to say that the left-hand side of this diagram, we have a cycle. Okay, we have a class. So on the top left, on the top left part, we can have some cycles, but on the bottom, we have some Hodge classes. And the thing we want to say that this map is not surjective on Hodge classes. So we're going to have some Hodge class here, which does not come from the cycle here. And the way how we're going to do it, okay, we're going to build a map. Okay, we have a volume map, the vertical map, and we have the horizontal map F, which I just described. And we just need a map phi, this capital Phi map, which is 0 on flags with F2 equals 0. that means that if you have a cycle here on the top left, we map the cycle to the flag by f, then this map phi would actually map it to 0 if the thing is commutative. So the first goal is to make this thing commutative and to make this map phi. It's a bunch of maps. So for each vertex, for each ray, we should have a linear map phi. That's roughly the idea. So there are a lot of these phis. You can count the number of parameters. Like you have a, so f0 is in 12-dimensional lattice and f1 is like in 4-dimensional lattice. So it's like whatever, 48-dimensional space of parameters here. And then we also have some linear part, but that's finite. Right? Okay, and this is what I said. So if you have a Hodge class, the Hodge class has to be mapped to 0 by the composition. But if you wanted to map to something to the Hodge, if you have a cycle, which if you have a cycle, the cycle is mapped to 0, means that we are not going to have a Hodge class of. Okay, that means what? That means that, of course, we cannot have this diagram commutative because we know there is at least one Hodge class which is represented by the polarization. So we want to make this commutative, but not commutative like on a nose, but commutative modulo the polarization at least, and maybe commutative modulo some proper sublattice of this three-dimensional lattice. All right. Let me write it down explicitly what we're trying to build. So this map this map phis, as I said, so they depend on two parameters. X is the vertex and U is kind of this array, and it's a linear map. So for every vertex and every array, we're going to have a linear map. Now we have the commutativity of the diagram is essentially two conditions. One is it's commutative for any triangle, and it's commutative for any parallelogram. So what happens with a triangle? With a triangle, what happens is that this triangle, as I said, it's mapped to 6 flags, and each of, so you see there are 6 terms, and each of those flags actually have this the common volume element of that triangle. So we are, and each of them of those flags would correspond some phi. So phi of that flag is a linear map, and so we have 6 of those phis, and they are evaluated on this volume element. And as I said, so the vertical arrow should give us the. By the way, the triangles with integral slopes will have to be equilateral, right? So you understand. I hope you understand that's all the sides of the triangle have to have the same integral length. Otherwise, it's not possible to make it integral slopes, integral directions. So this is s squared. So I think I multiplied by 2 for some reason. So it's actually 1/2 of that. If you, well, it depends on how you think of an area. And then, okay, this is the volume. And the second equation for the parallelogram. So now we have 8 flags, and we evaluate the flags at those volume element, which is again the same. So U and V now are not necessarily the same length vector. So we now have S and T are the lengths of them. The parallelogram can be, arbitrarily lengths. They don't have to be same lengths. So anyway, so these are the 2 conditions. Very explicit. You can try to run, your computer So I did try a little bit of trying to solve this problem. So I've used some. I mean, I did some answers of that. So I've assumed something about those map phi, essentially, which makes this problem kind of finite dimensional. So I've assumed some very strong condition that it's not how this fineness changes as I move the vertex, and this is the assumption which I've done. As I move a vertex to another vertex along this ray, then I want it to be kind of linear. I mean, this difference to be linear, and that's already enough to make this problem finite dimensional. So there are some co-cycle condition and everything. So everything is now determined, and you try to solve this system. You can solve this system in gamma 0 times gamma p. That's no problem. But now you try to make your solution gamma 1 periodic, right? So you want x to be living on a torus, the point x. And this is where you come with sort of some finite set of, I think it's 96 equations or something like that, linear equations. So you try to solve them. And well, you can solve them, but you cannot actually solve them modular any proper sublattice. Then so you're gonna kill both the polarization class. I mean, you know, you have to kill the polarization class, but you turns out that the solution only exists when you also kill the W1 and W2. So that's not a counterexample. All right, but you're welcome to try. And all right, thank you. I'll stop here.
Okay, thank you, Ilia. Jane, I think you can stop recording.